Hello and welcome back to Unbounded Operators, the video series where we continue talking about topics of functional analysis. In particular, we talk about the general concept of operators, which also can be unbounded. And as we have already learned, in the general unbounded case, we usually have to specify the domain of definition for the operator. Indeed, different domains can lead to different properties of the operator, and therefore we cannot avoid talking about these domains. And in today's part 9, we will see that choosing the largest possible domain is not always the best choice. However, before we start with this discussion, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can download a lot of additional material with the link in the description. Okay, then I would say let's immediately fix the assumptions of this video, namely we consider two Banach spaces x and y. And between these two spaces we can take a linear operator, which we usually call T, and we also assume that this one is a densely defined operator. As you know, this simply means if we take the closure of the domain dt, we get the whole space x. And this is all we need to get the so-called adjoint operator T prime. However, now this T prime goes from y prime to x prime, so it changes the direction, and it also considers the dual spaces. This is important to note. Formally, this adjoint operator acts on different spaces than T. So this is what we can do in a Banach space, but you might remember special Banach spaces are so-called Hilbert spaces. So let's put this on the right hand side, the special case that our Banach spaces are also Hilbert spaces. Then the notion of a densely defined operator does not change at all, but we can have a different approach for an adjoint operator. And we already know this one, we call it T star. There we also change the direction, so we go from y to x, but we don't have the dual spaces involved at all. Hence, this adjoint operator is easier to deal with because we don't change the spaces that are involved. However, since Hilbert spaces are just special Banach spaces, we actually have two adjoint operators for an operator between Hilbert spaces. This means if there is a danger of confusion, we would call the left-hand side the Banach space adjoint and the right-hand side the Hilbert space adjoint. But as we have learned in the last video, both adjoints are actually quite similar. The connection is immediately given by the so-called Riesz representation theorem. This one tells us how the dual spaces look for Hilbert spaces. They are quite similar because we find an isomorphism between x and x prime if we have an Hilbert space. Indeed, this one we have proven in the functional analysis course. More precisely, what we have here is an antilinear isometric isomorphism. And there antilinear means conjugate linear, so it only matters for complex Hilbert spaces. However, for these we have a complex conjugation involved, which we cannot just ignore. In fact, in examples you will always see this complex conjugation when we talk about T star, but not when we talk about T prime. And now maybe we give this special isomorphism a name, let's call it C with index x. This means this is our conjugate linear map that sends x to x prime. And there you might remember that this is quite simple, we just send a vector x to the inner product. And then on the left hand side we have our vector x, and on the right hand side we would put in our argument for our linear functional. So in order to keep it simple, we just put a dot there. And often it's clear that we talk about linear functionals, and then there is even a shorter notation for that. Especially physicists use that a lot, they just write the brackets from the left and then a vertical line. Maybe in this video we also use that short notation, but just remember it represents a linear functional in x prime. Moreover, on the other hand, we can also do the same for the second Hilbert space y. It's exactly the same, but there we have to use the inner product in y. However, also there, let's shorten the notation. Okay, and now with these two antilinear maps, it's quite easy to make our connection between the two adjoints T prime and T star. So maybe let's make a quick sketch. Here on the left we have our Hilbert space y, and then T star acts on it, and what we get is something in our Hilbert space x. On the other hand, the corresponding dual spaces we can put to the lower level. And there we know, in between we have just our T prime from Y prime to X prime. So apparently our translation here is quite simple, we just have to apply our C operators. And then we can actually check if we get the same result in both ways. More concretely, we want to consider the following composition, first applying Cy, then T', and then going back with our Cx inverse. This means what we put in here is a vector y coming from the domain of T star. This is important because only these vectors we can put into T star at all. And indeed we immediately see that the whole thing here is not complicated at all. What we have is T' of our linear functional of y. Therefore now the question is this linear functional in the domain of T'? And from the last video we already know that there's a defining equation for these functionals if we put in a vector from the domain of T. More concretely, we take the functional and apply it to the vector Tx. However, now the functional is just the inner product, so the whole thing looks like that. And now we can use the fact that y comes from the domain of T star, which means we can pull T to the other side. Hence there we have T star y on the left hand side, which means now we have a linear functional in x prime. In other words, this is exactly what we want to use on the right hand side now. This means our T' is gone and now we have T star in the equation. Namely, in the short notation we can just write T star y. And obviously this one we can immediately translate by using our antilinear map Cx. Namely, we get immediately our T star y. Hence our connection is now completely clear. T star is simply given as Cx inverse T' Cy. So exactly what the picture suggested before, and we also recognize that the domains fit in as well. Okay, so this is the important operator equation you should remember when you want to translate between both adjoints. This is important because sometimes you might see a result written for the Banach space adjoint, but you actually need it for the Hilbert space adjoint. And now you know this is not a big problem at all, because you can just do the translation as we did it here. So for example here, let's formulate an extension result for the Banach space adjoint, which also holds for the Hilbert space adjoint. And what I want to say here is, if you take the operator T and extend it to a bigger domain, so let's say we have an operator S, and we write the symbol to say that S is an extension of T. Hence we have the subset relation between the two domains dt and ds. Moreover, if we restrict both operators to the smaller domain, then they act exactly the same way. So this is important to remember. This is exactly what we mean by extending an operator. So you see, it's definitely helpful to put all this information into this short notation. So here maybe it's possible to extend this operator T by increasing the domain. But then, and you could see that as a disadvantage, we get the opposite result for the adjoints. So now T' could be bigger than S'. Or to say it in the same words as before, now T' is an extension of S'. But if you want to read it the other way around, you would say that S' is now a restriction of T'. So this is important to remember. If you make the domain bigger on the one side, you make it smaller in the dual spaces. And now we already know the same result we get immediately for the Hilbert space adjoints as well. And in this formulation you might already recognize that for self-adjoint operators, where we want to have T is equal to T star, the correct choice of the domain is key. Of course we will talk about this even more later, but at the moment you can already see just choosing the biggest possible domain for your operator might not be the best choice in the long run. Simply because in the end, the adjoint could have a really small domain. Now maybe surprisingly, the proof of this proposition is quite simple because we just have to use the definition of our domain. So please recall this from the last video. This one here is the domain of S'. And the key thing is that we have to satisfy this equation here for all x in the domain of S. This means this equation is definitely also satisfied if we make the domain smaller, so if we choose the domain of T. Hence, in the second line here, we have to check less vectors, and therefore the whole set here can only get bigger. Or to say it more precisely, it cannot get smaller. However, now on the smaller domain, instead of S, we can also just write T of x. Hence what we get now is simply the set dt prime. And that's it. This is all we have to do. Now we have proven that this domain is actually smaller or equal than the original domain of t prime. So that's it, and I would say we should definitely look at examples with the next videos. So I really hope we meet again and have a nice day. Bye bye.
God